advantage of that. And she said, my worry though is that every school will start increasing its requirements to get in and scholarship requirements. You know, it's possible. It makes sense. I'm like, mm-hmm. It costs more money to do it that way, but that's, I mean, it could get you thousands of dollars to go to college on, so it could make a difference. All right. I don't know. That's a lot of politics involved in that I'm not sure I'm qualified to even discuss. All right, so we're going to talk about rational expressions and rational functions this evening. And rational expressions and rational functions are just big old fractions. That's what we're going to be dealing with, is fractions that have polynomials in the numerator and denominator out of that. So when we're dealing with rational functions or rational expressions, we talk about the domain. The domain of a rational expression slash function. When we do the next section, they change the name to functions and put an equal sign beside it. Should be found before the fraction is simplified. Well, simplified has an I. That's why my reading score is so bad. Simplified. All right, so we're going to find that domain before we simplify, and then we're going to do some simplifying, and that's where the factoring comes in, is to the simplifying and also the domain. So when we talk about domain, what are we talking about as far as a function goes? What part is the domain? The x values. And back in 100, we talked about finding the domain of a function, and there were two red flags that could come up that were important when finding the domain. Does anybody remember what they are? Say it again. Okay, that makes something a function. If you got a list of ordered pairs, you can't repeat x values. What was the thing in an expression or in an equation that was a red flag and caused you to have to find the restrictions on the domain? The radical with an x inside of it, so a square root or a cube root or something like that, or x's in the bottom part of the fraction. That's the things that made domain different than all real numbers. Okay, so we're dealing with rational expressions tonight. So that's going to be the fraction with the x's in the denominator. That's what we're going to be dealing with. So let's look at a function or an expression first. So we're going to find the domain. And simplify. First example is going to be factored for us already. Okay, so when we were going to find the domain, the red flags were square roots or x's in the denominator. And if an x was in the denominator, that was the red flag that said, okay, you got to do something. What you've got to do is take the denominator and set it equal to 0. So x minus 1 times x plus 3 equal to 0. And then solve that. And if it's in factored form, solving it's easy. You just take each individual factor and set those equal to 0. Get x equals 1, x equals negative 3. So our domain would, in set notation, is all x's as long as x does not equal negative 3 or 1. In set that's in set notation. In interval notation, you'd go from negative infinity to negative 3, union, negative 3 to 1, union, 1 to infinity. So set notation, interval notation. Work back and forth between the two. Let's see, bouncing back and forth. Now, the last step in this problem, so we found the domain by taking whatever's in the denominator, set it equal to 0 before you simplify. Then the final step is to simplify the fraction. So what cancels out top and bottom on that fraction? Well, look what matches. Got matching factors right there. We get -1 and x minus 1. Those matching factors cancel each other out. And then the simplified version only has x minus 7 on top and x plus 3 on the bottom. The simplified version only has that. Now, if we had simplified first, we would be missing part of the restrictions on the domain. Okay, so that's why we find the domain before we simplify. Okay, find the domain before you simplify, and then do your factoring and simplify. So let's go to one that's not so cakey. So this one's not factored for us. But again, we're going to find the domain, and then we're going to simplify in that order. So domain has to be done first. So the red flag that comes up here is that we have an x in the denominator. So the rule is to set that denominator equal to 0. And because we're setting that denominator equal to 0, we've got all the options as far as how we solve that. Now, what you want to do, though, is really factoring is the method you want to try to use to solve it, because you're going to have to use factoring to simplify it. So if you can use that to solve it, it's going to be one less thing you've got to do when you go to simplify. So that's why we spend a little time doing factoring to see. So let's try to factor x squared minus 25. We've already done that once this evening. So what does it factor as? Yep. X plus 5, x minus 5. Good job. And then we set each of those equal to 0. So x equals -5, x equals +5. So our domain is going to be all x's as long as x does not equal plus or minus 5. That's the easy way. That's the set notation. Let's get the interval notation for that. -infinity to -5, union -5 to +5, union 5 to infinity. So there's our domain. And then we want to go and simplify our fraction here. So I've already got the factored form of the denominator. So I'm going to use that when I go to simplify this. I'm going to write that fraction, x plus 5, x minus 5 on the bottom. And then I'm going to try to factor the numerator as well. So I'm going to use the x method to factor the numerator. Multiply to be 5, add to be -6. What two numbers would do that? -5, -1. I can use my shortcut here. X minus 5, x minus 1. So there's the factored form of that numerator. Then the simplifying comes in. Matching factors cancel each other out. X minus 5 cancels x minus 5. Get x minus 1 over x plus 5. Factoring gets you all kinds of stuff. Domain has to be found before you factor. Okay, keep that in mind as we go throughout the entire unit here on rationals, that if we're going to find the domain, we got to do that before we simplify. Okay. I'm not going to make you find the domain on every single problem we do tonight. Okay. Just remember, if it does ask for the domain, do that before you do anything else. Don't do anything else first. Domain happens first before you do anything. Okay. All right. So let's go into the mode where we're just simplifying. I'm not asking you for the domain. I just want to do the simplifying stuff because that takes that factoring skill that we worked on earlier and makes us really practice it a lot. So let's just simplify. We're not going to find the domain, but we know if we needed to find the domain, we do that before we simplify. That's what we know. Okay, so we're going to simplify through 4 here. 12x squared minus 30x over 4x squared minus 25. So we're going to try to simplify this. And in order to simplify, you want to factor in every way possible everything that's in the problem. So let's just start with the numerator. And how could I factor 12x squared minus 30x? Can't do that on the top. I mean, the bottom is, but the top is not. Because one of them's got x squared, the other's got a plain x. So what's the first thing that I always look for? Greatest common factor. What do 12 and 30 have in common? 6 goes into both of those. And they both have an x, so it's going to be 6x. What's that leave in the parentheses? Good job. Then the denominator now, to factor that, I am thinking difference of squares. I know 25 is 5 squared. 4x would be 2x squared. So my factors for that would be what? Yeah, 2x minus 5, 2x plus 5. Which ones of those cancel out? Yeah, the 2x minus 5s cancel each other out. This one cancels that one, leaving a 6x over 2x plus 5. The x's cannot cancel each other out here because this x is tied to the plus 5 with the 2x in front of it, and this x is not the same. The factors have to match exactly to be able to cancel out things with x's. So this one doesn't match because this factor is 2x plus 5, and that factor is just 6x. They've got to match perfectly to be able to cancel out, and they don't. And there we have the simplified version of that. Okay, so simplifying just takes factoring. Really all it takes. Let's do another. X squared minus 8x plus 16 over 8x minus 2x squared. So a little curveball on this one. We're looking at it. So we were finding the domain. We work with the denominator first, and we're not having to do that here. So we're just going to simplify by factoring everybody as far as we can, and then canceling stuff that matches. So the numerator looks like it's already ready to factor. So I'm going to do X method and factor it. Multiply to be 16, add to be -8. What does that? Yeah, -4 and -4, so that'd be x minus 4. And you could write x minus 4 squared up there if you wanted to. I'm going to go ahead and write them out both because I may need to cancel some stuff out. So I'm just going to write it out like that. Whoops. And now, the denominator, what's wrong with it? Not in descending order. So let's get it in that order first. So I'm just going to rearrange it right underneath that. Put the -2x squared plus 8x. So putting it in descending order, and then what can I do to factor that? Greatest common factor, which would be 2x, and because the leading term there is negative, I'm going to pull a negative 2x out. Okay, anytime the leading term is negative, you want to pull that sign with it. So if I pull out a negative 2x, that'll leave us x minus 4 in the parentheses. So yet another reason why we want to do that is because we can see what's going to cancel there. How many of those x minus 4s will cancel? This 1 on the bottom cancels 1 on the top. We get x minus 4 over negative 2x is the simplified version of that.
Whenever we write those out as a in a problem, do we need to put the simplified version? Do we need to put those in parentheses, like x minus 4 in parentheses?
Only if there was more than one thing on the top or bottom. Like if there were another factor left, then you would need parentheses around them. But if it's the only thing that's there, you don't have to. Doesn't matter if you do. If you're doing it on the lab, I'm not going to count it wrong either way. But if it's got more than one factor, they are needed. We'll get to might find one that has that. They don't get too complicated in this particular section with this stuff. So, but yeah, parentheses kind of optional since there's only one thing left on top or bottom. All right, good question. E, 2x squared plus 7x minus 4 over 5x squared plus 20x. Okay, so I'm going to factor. I want to factor the denominator first because it's easier. So what do we do with the denominator? GCF would be 5x and x plus 4. And then I'm going to go to the numerator and do the x method on it. We're just doing a lot of factoring, and it's really the name of the game tonight with this section. It's just tons of factoring. We need something that multiplies to be negative 8, adds to be positive 7. What does that? Good job. 8, negative 1. And I can't take the shortcut with this one because it's got that 2 in the front. So I'm going to have to somewhere put 8x in there and 1x and then group. Maybe you can do that in your head. Obviously, I'm not doing it in my head. So we got 2x minus 1, then x plus 4. Love it when a plan comes together. The x plus 4s cancel out. And again, you cannot cancel this x with that x because this is tied to in part of a different factor. They've got to match exactly the same for that to happen if there's pluses or minuses involved. Questions about those? Okay. Well, let's add a little something to the game. Since we're just dealing with rational expressions, let's do a little bit of multiplying. So let's go back old school here and do a nice little easy 3rd grade fraction multiplication. Maybe 4th grade. I know you do fractions in 3rd grade and multiplication, but I don't know if you multiply fractions. So why are we doing this? We need to remember the rules of multiplying fractions and what's allowed and what is not allowed. Okay? So what is allowed when you are multiplying fractions together? What are the things that you're allowed to do? The most basic way of multiplying fractions is top times top, bottom times bottom, just go straight across. And you'd say 6 times 21, pretty big number. And then you'd say 7 times 30 is 210. And you would get that fraction, and then you'd have to reduce it. That's the most basic way of multiplying fractions. But we're smarter than that. There's ways of reducing as we go. What are the rules for multiplying fractions? Which directions can you reduce? Well, could I reduce this first fraction up and down? 7 and 6. Do they have anything in common? What about 21 and 30? 3 goes into 21 7 times. So I could reduce that to 7 over 10. So I can reduce vertically inside the multiplication problem. How else can I reduce? Can I reduce side to side? No. This one I couldn't do that anyway with the numbers, but it's not allowed. But I can reduce diagonally. I remember the words cross cancel. Remember that term is used a lot in elementary school along the way. You can cross cancel, so that means diagonally that you can cancel out terms or factors. So 6 and 10 are both divisible by what? 2. 2 goes into 6 3 times and into 10 5 times. And then what about 7 and 7? By 7, yeah. Both of them divisible by 7. Once you've done that mess, all you got to do now is take those really small numbers and multiply across. 3 times 1 is 3. 1 times 5 is 5. A lot easier when it comes to the reducing to do it that way than it would be to say 6 times 21 is 126. And then 7 times 30 is 210, and then have to reduce 126 over 210. That would be difficult. Where that comes into play with polynomials is you definitely would not want to multiply to make a bigger polynomial and then have to factor a bigger polynomial into its smaller parts. So let's start with something like this. 6x to the 4th over 7 times 28 over 9x squared. So not a big polynomial, not a whole lot of factoring involved here, none actually. It's just multiplication involved. So let's take the same idea. I'm just going to add some x's to it. Can the first fraction be simplified vertically? 6 and 7 don't have anything in common. What about the second one, 28 and 9? Nothing. Okay, so we can't do vertically on this one, but can we do horizontally? Well, I mean, not horizontally. We never can do horizontally. What about diagonally? 6 and 9. What goes into both of those? 3. 3 goes into 6 twice, into 9 3 times. And then what happens to our x's there? We got an x squared and an x to the 4th. Go down by how many though? And we got 4 up top and 2 on the bottom. What happens? 2 of them cancel it out, right? We've got 2 left. So the x squared is going to be up top. So this x squared down here, it's gone away completely, and this becomes x squared up here. So 4 of them get canceled, 2 of them get canceled. And then diagonally with the 7 and the 28, 7 goes into itself once, and then the 28 4 times. Now all I got to do is multiply across. 2x squared times 4 is 8x squared. 1 times 3 is 3. I think sometimes I've seen in this course and my college algebra classes that I teach, math 140 and stuff, a lot of times these problems give you more trouble than the big polynomials that you got to do X method and factoring and stuff. I don't know why, but it just seems like that's what happens. All right. Let's do one more of those, and then we'll get to some we got to do some factoring. Let's say we had 4y squared over 18 times 27 over 8y to the 5th. Similar problem there. Can we do anything vertically? First fraction, 4 and 18 are both divisible by what? 2. So I'm going to simplify that way first. So that'd be 2 over 9. And then the second fraction, nothing happens. 27 and 8 don't have anything in common. So now I start looking diagonally. So this direction. 2 and 8 definitely has something going on. So 2 goes into itself once, into 8 4 times. And how many y's get canceled out? 2, and there are how many left over? Where are they at? They're on the bottom of the second fraction, right? So it's y cubed down there. So this goes away, and this becomes y to the third. And can I cancel any diagonally this way? Yeah, 9 goes into itself once, into 27 3 times. And now I got an easy math problem. 1 times 3, 1 times 4, y cubed. And if it starts getting to be too much of a jumbled mess, don't think you can't rewrite the problem and start right in the middle. Okay? So sometimes it gets to be a jumbled mess. I have the luxury of using different colors. That helps me know where the steps are and what color I'm using at the time. Helps a little bit sometimes. So color pencils can be your friend if you like to be creative with your math, but not required. But don't think you can't rewrite the problem. Rewrite it. If you want to just do one step at a time, that's fine. All right, so let's get into multiplying larger polynomials together where we got to do a little bit of factoring. So let's say for example, we got x squared plus x minus 12 over x minus 3 times x plus 5 over x squared plus 3x minus 4. Okay. So, bless you. They've given us a problem here where we've got some trinomials in there, and then we got a couple of binomials that don't factor at all. So we need to do the factoring. So the idea here is just factor everything that's there. Before you start doing anything else, just get everything factored as far as it'll go. So I'm going to do X method on the top left. Multiply to be negative 12 and add to be 1. What does that? You got coronavirus. What will that be? 4 negative 3. Good job, Ben. So 4 negative 3. So that's going to be x plus 4, x minus 3 on the top. The bottom part I know doesn't factor because it's just x minus 3. So I'm just going to rewrite it there. I already see something that's going to cancel, but I'm just going to be patient and wait and just do all my canceling at once. Then I'm going to do X method on the denominator of the second fraction. Okay? X squared plus 3x minus 4. So it'd be negative 4 up top, 3 on the bottom. What numbers do that? Four and negative 1. So that's going to be x plus 4, x minus 1. So nice to us there. We didn't have to do any grouping or anything to do our factoring. And now that I've got everybody factored, I can do the same rules that I used before. Vertically or diagonally. That's the only ways I can cancel. So I always go vertically first for no apparent reason. Maybe that's the way that my high school teacher taught me to do it first. I can't remember. But that's just the way I've always done it, or especially since I've been teaching. So I go vertically first. So I've already seen this one, so I've been itching to mark that one out. And then I don't have any other verticals that could happen, so I go diagonally. What can cancel diagonally? X plus 4s. Everything over here on the left fraction went away. What really is that now? Not 0. It's 1. It's kind of like if you had 7 over 7, right? Everything, it reduces to be 1 over 1, technically. So all we got left, though, is these two things. X plus 5 over X minus 1. And you got to simplify. That's it. If we had to find the domain, where would we have done that? Before we simplified, we'd have taken all of these denominator pieces and set them all equal to 0, and we've got 3 different pieces that couldn't be, that X could not equal for our domain, if it asked for that. Most of the time on multiplication problems, it's not going to ask for the domain. That's only going to be like a single fraction issue. So multiplication problems usually just simplify problems. But if they did, for some reason, maybe on the final exam, decided to put a problem like that on there, you know, domain happens before anything else happens. That's always the case. All right, let's take example J. 4x squared plus 3x minus 10 over 2x squared plus 3x minus 2 times 4x squared minus 1 over x plus 4. Fun. All right. What do I do? X method on the first fraction on top and bottom, right? So I'm going to have to do that. And I'm also going to have to do some grouping. So I'm just going to do that stuff, you know, down here somewhere and like scratch work. So what goes on top of my x for the numerator, the top part? That's where I'm at, is up here with the 4x squared minus, or plus 3x minus 10. What goes up top? Negative 40, add to be 3. 8 and should be negative 5. And I can't take the shortcut because it's got that 4 in front of x squared. So that's where I got to do a little extra here. And group 4x, x plus 2, negative 5, x plus 2. So my numerator is factoring as x plus 2 times 4x minus 5. 4, so that's the numerator of the left fraction. Let's get the denominator using the same methods. Negative 4 had to be 3. That smells like something we've already done before there. So that'd be 4 and negative 1. But it's different because I got to do the grouping. I'm going 2x squared plus 4x minus 1x minus 2. We're grouping those two together. So that's going to give me 2x minus 1, x plus 2. So we've got the first fraction factored. The second fraction, good news is the denominator doesn't need any factoring. So I'm just going to go ahead and copy it down. But the numerator does. It's, what is that? Yeah, it's a difference of squares. So that's 2x plus 1, 2x minus 1. Once I get everybody factored, that's when I can start canceling stuff out. So My numerator has 4x minus 5. And so, Amber, this is kind of related to what you asked about earlier. Because there's more than one factor left up top, I'm going to put both of them in, each one in parentheses. And you don't have to multiply it back out. Just leave them in parentheses. I don't need you to multiply it back out. 2x plus 1. And the denominator's just got the x plus 4. So this is our final answer. That's our simplified version of that. You don't have to multiply the numerator back out. No sense in that. Okay. All right. One last thing in this section, and then we'll get on to the next one. Division. So we're just going to do this quickly. So what letter are we on? I don't know. Okay. Let's say we're going to do 2/3 divided by 15 over 4. Do y'all remember the rule for how to divide fractions by hand? Which one do you flip? The 2/3 or the 15 over 4? The second one. Yeah, that's right. So 2/3 times 4 over 15. And then you've turned it into the same problem we just did, right? The same kind of problem. You cancel vertically or diagonally. So diagonally, nothing seems to be canceling here. So that'd be 8 over 45. There's that one. So division, flip the second one, and then do the exact same thing we've been doing. Nothing different, okay, other than the very first step. Always flip the second one, though. The second one is the one we're flipping. And go from there, okay? So nothing, I don't think we need to go over one of those. All right, so let's go to the next section, which takes our same idea and throws us from the review chapter in our textbook all the way to chapter 3, toward the end of chapter 3, and gets us to 3.5, which is rational functions. And it also talks about the graphs of those, so we're going to talk about that a little bit too. All right, a rational function, the most basic rational function, we call it the parent function, is 1 over x. If I were to graph 1 over x with my calculator, I'm going to show you what that looks like. 1 divided by x. Whoa, get zoom 6 here. There we go. That is the graph of 1 over x. That's what it looks like. So that's the general shape of the things we're going to be graphing in this this particular section. All right. So now, from this graph, we can talk about the domain. We can also talk about the range because we're dealing with a function now and not just an expression. Domain exists in expressions. Range comes on board when we start talking about functions because we got x and y related to one another. That's what makes up a function, is the relationship between those two. So the domain, generally, for the parent function, you would set the denominator equal to 0. And it's only x, right? So x can't be 0. And then your interval notation for that would be this. We're obviously going to get more complex than that later on. The range for this happens to have a horizontal asymptote, which we'll talk about those in just a minute, at 0. And I'll show you, we'll go over rules about when the horizontal asymptote is a certain number and when it's something else as we get through this section. So there's a lot of background we're going to get into here. So there's the interval notation for your range. We're just taking 0 out of it. So this is all for that particular function, 1 over x is what that stuff is. Now, there's a vertical asymptote at x equals 0 and a horizontal asymptote. And I'm going to show you these on the graph. at y equals 0. So those are where these are at for the 1 over x function. It changes depending on what the function is, where those are happening at. But if you look at the graph, you can see these places. I'm gonna hit y equals, and I'm gonna graph the y equals 0 asymptote there. That's that horizontal one. You can't hardly see that. I wish it was a different color. The horizontal asymptote at y equals 0 goes right here. Notice how that graph kind of gets up here and starts hugging the x-axis. Doesn't ever really get there though. So what that is it's a boundary line. An asymptote is a boundary line that kind of guides the graph in the way to go. So the horizontal asymptote for this one is at y equals 0. It guides this line and kind of steers it in that direction. The blue line never touches that y equals 0 though. It's an asymptote, it's a boundary line. The vertical asymptote is at x equals 0. And we can see how this kind of hugs that line too. It's also a boundary line. So asymptote's a boundary line for our graph. And we're going to learn how to find those in this section and a few other things with this out of that. But those things, that's the general shape. We're going to pick that shape up and transform it next. So shifting up, right, left, up, down, left, right. And then stretching and compressing and all that fun stuff that we did way back. So we got to remember those transformations that we talked about. So let's do that first, and then we'll get into some of the rules of how you can know where those asymptotes are and that sort of stuff for different functions. So let's do some transformations on f of x equals 1 over x. Okay. First example, g of x is equal to 1 over x minus 2. You guys remember the rules about transformations. If it happens on the outside, what kind of shift is it? Remember us talking about this in 100, the transformations. Things on the outside are what? Versus things on the inside are this other thing. Outside is vertical, inside is horizontal. Okay, remember outside is vertical, inside is horizontal. This is an inside job here because that minus 2 is in there with the x in the fraction. So this is a minus 2 on the inside. So that's going to shift it right 2 units. If we go to our graphing calculator and go to y2 and I type in 1 divided by parentheses x minus 2, there's the original. There, the one next to it is shifted to the right 2 units. So we can look at the graph and kind of see some of this stuff, but we want to be able to just look at the equation and be able to tell what's happening to it. Okay, so if it shifts the function to the right 2 units, where is that vertical asymptote at now? The original was at 0. So it's at, what is it? At 2, at x equals 2, because we're shifting to the right 2 units. If it shifted it to the left 4 units, it'd be at -4. Okay, so shifting it it changes where those asymptotes are. It changes the domain of our function, because instead of x can't be 0, if we look at the function, we set that denominator equal to 0, x couldn't be 2, right? So that's where that vertical asymptote comes in as well. Okay, so sometimes they can ask some questions like that just take a little bit of thinking involved. All right, let's take this one, g of x. So again, based off the original graph, what if they did this, 1 over x plus 5? What shift does that do? Is that on the is that plus 5 inside with the x or on the outside of the fraction? It's the outside of the fraction. So outside, remember, is a vertical shift. So if it's plus 5, it's going to go up 5 units. Okay. Been a while since we've done this, so by all means, it's review kind of stuff. So I'm you don't do this every day, as I've said before. Nobody's going to ask you to do this at Food Giant, so it's not something you do every day. I understand if you don't remember everything that we've done. All right, let's get what if this one 1 over x plus 3, and then a minus 6 after that. What transformations have happened there? Left 3, down 6. Good job. So that's going to put our vertical asymptote at -3 and our horizontal asymptote at -6, which changes our domain and range out of that. One more. G of x is equal to 4 over x plus 1. That'd have to be a negative sign to be a flip, be a reflection. What's the 4 do? I think we know what the plus 1 does. What's the plus 1 do? Up 1, right? This 4 is the one. What's up with the 4? What happens when you? How did that 1 over x become a 4 over x? Remember, we started with 1 over x. So to become a 4 over x, you had to have multiplied that dude by 4. Because if I multiply that by 4, 4 times 1 is 4, and 1 times x is x. So that's what's happening. What does a 4 multiplying by a whole number 4 do to the silly putty? Remember my silly putty example for this? Y'all may not have. If you pull it this way, that's a vertical stretch, right? If you pull it this way, that's a horizontal stretch. And if you push it in, it's a compression. What does multiplying by a big number do on the outside? Remember, outside. It's a vertical movement. So the big number is going to be a vertical stretch. So vertical stretch. A horizontal compression would be, you would have 1 over 4x like that. That would be a horizontal compression out of that, not a vertical, because that's inside with the x. Remember, inside is horizontal movements, outside is going to be vertical movements. Okay, so a little bit of review of transformations. We don't hang our hat too much on that in this section. We're going to do the other stuff a little bit more than we do that. So let's talk about some important parts of rational functions. So these are the things that one needs to memorize for this particular set of material that we're doing here. So important parts of rational functions. Okay, important parts of rational functions. The first one is obviously what we've already done with the domain. And to find the domain of a rational function, what do? How do you find the domain of a fraction? All right, set the denominator equal to 0. When do you do that? When do we find domain? Before simplifying. Okay. Domain, set the denominator equal to 0 before you simplify. you want to try to factor to solve that, because that's going to help you do the simplifying step after that, okay? So domain, set the denominator equal to 0 before you've simplified the fraction, okay? And then, so the first thing you're going to find is the domain. The second thing you're going to do is simplify the fraction. And you're going to do that by factoring and cancel matching factors. Just like what we did earlier. So that's always going to be your next step, is to simplify the fraction if possible. Some of them won't simplify any further, but we've got to check to see if it will before we proceed. So we're finding the domain. We're going to simplify the fraction and then go from there. After we've simplified, the next thing that we would look for are the vertical asymptotes. Vertical asymptotes are those boundary lines that show restrictions in the domain and range. They shape our graph. They are found by taking whatever's left over in the denominator, setting it equal to 0 after you've done the simplifying step. Sometimes it will be exactly the same numbers as your domain. Sometimes it will be a little less than that. They won't have all of those pieces because some of the factors may have canceled out, okay? So vertical asymptotes are the easiest asymptotes to find, because you're just going to take whatever's left over in the denominator after you've simplified and set them equal to 0 and solve them for x. They're going to be equations that say x equals something, okay? That's what your vertical asymptotes are going to look like, because the equations for a vertical line is x equals a number. That's the reason it's going to be x equals always for vertical asymptotes. X equals a number, okay? We'll get to how that happens in just a little bit, okay? Or work on practicing that. All right, now, the next type of thing that we're going to find is the horizontal asymptotes. And this is a little tougher sometimes, and sometimes it's easier because there's rules that go with horizontal asymptotes. Horizontal asymptotes. Again, the asymptote just means that it's the boundary line that shapes our graph, okay? Horizontal asymptotes. There are scenarios in which you will have different horizontal asymptotes. The first rule, or the first scenario, we'll call it scenario A, is if the degree of the numerator is less than the degree of the denominator. Then the horizontal asymptote is y equals 0. When I say degree, what am I talking about for the numerator and the denominator? Let's write an example of a function that does that. Let's say we had x squared plus 5x minus 7 over x cubed plus 6x squared minus 2. Something I know doesn't factor. This is an example of that happening. Okay. The degree of the numerator is 2. The degree of the denominator is 3. So where does degree come from? The exponents on the variables. The degree of the numerator is the highest exponent on a variable in the numerator. The degree of the denominator is the highest exponent on the variables in the denominator. This can be decided even before you simplify. Okay. In the original form of the problem. It doesn't change once you simplify. It's still the rule about the horizontal asymptote doesn't change. It will always stay the same after in either the original form or the simplified form. It always stays the same. Okay, so degree smaller on top, y equals 0. Automatic, no calculation required. That's easy, right? That's the easy one. That's a good scenario. We like that to happen. Let's get scenario B. If the degree and I'm going to write HA is y equals 0. If the degree of the numerator and denominator are equal, then the horizontal asymptote is at the ratio of the leading coefficients. Okay. Example of a function that does that would be something like this. F of x is equal to 3x squared plus 5 over 4x squared minus 2x plus 13. The degree of the numerator is 2. The degree of the denominator is also 2. They're equal. So the horizontal asymptote is at y equals the ratio of the leading coefficients. The leading coefficients is the number in front of the variable with the highest power. So 3 over 4. That's the horizontal asymptote. So scenario A, degree on top is smaller than degree on bottom. Then it's at y equals 0. Degree on top and bottom are the same. It's at 3. It's at the ratio of the leading coefficients. In this case, 3 over 4. Okay. Those are the two scenarios for horizontal asymptotes. That's the only time horizontal asymptotes occur, is when it's those two rules. Okay. Vertical asymptotes, we're usually going to have those. Horizontal asymptotes, we only have them if the degree of the top is smaller than the bottom or if the degrees are equal. That's the only time horizontal asymptotes exist. Okay, so maybe that's easier than the vertical asymptotes. I don't know. Now, the next type of thing that could happen is we could have what's called an oblique asymptote. Where are we at? Number 4, 5. The fifth thing that we've got to look for is an oblique. Oblique. Oblique and you will sometimes, if you Google this and want, you're looking for some extra help on this somewhere, slant asymptote is the old name for these. That's the way I learned them. So you may hear me slip up and call it a slant asymptote. They're the same thing. Oblique asymptotes are diagonal in nature. They exist if the degree of the numerator is one more than the degree of the denominator. Then there is an oblique asymptote. It will have the form y equals mx plus b. Okay. Now, what are our rules for horizontal asymptotes? Degree on the top is smaller than the bottom. Degrees are equal to each other. Does this fit either of those scenarios? No, it's a completely different scenario. It says the numerator is one more than the denominator. So can oblique and horizontal asymptotes ever coexist? The rules say they don't exist at the same time, ever. Okay? You will never have an oblique asymptote and a horizontal asymptote at the same time, ever. When you're dealing with rational functions, never will that happen. Okay? So keep that in mind. Obliques and horizontals, you're only going to have, you could have one, you could have the other. You may not have either of them. Okay? Because that could happen as well. So an example of a function that has an oblique asymptote will be something like 3x cubed plus 5x squared minus 7 over x squared plus 6x minus 10. That would be an oblique asymptote scenario because the degree of the numerator is 3, the exponent on the x is 3, and the degree of the denominator is 2 because the exponent on the x is 2. That's 3 is 1 more than 2. So those are oblique asymptotes. To find the equation of the oblique asymptote, you have to do long division. And we did this in 100 very sparingly. We didn't do it very much. But it is a skill that we got to have. So let's do a little long division here. We're going to divide x squared plus 6x minus 10 into that function, that polynomial, 3x cubed plus 5x squared plus 0x minus 7. If you remember, if there was a missing piece, you had to put a 0 in its place. So this was along with the same sections that you did synthetic division in. You guys remember doing the synthetic division where you put the number up on the shelf and do that thing? Well, it's the same section as that, but doing the long division. So got to kind of review you on how to do that. So the first thing you do is you look at the first term of each part of the function. So x squared and 3x cubed. What times x squared would get me 3x cubed? 3x. 3x times x squared is 3x cubed. 3x times 6x is 18x squared. 3x times negative 10 is negative 30x. And then I'm going to subtract that whole thing. Does that look completely foreign to you, or do you kind of remember doing that? Hopefully you kind of remember. If you don't, it's not a hard thing to pick up. Just takes a little practice. So then we're going to subtract. The x cubes go away. 5 minus 18 would be negative 13. 0 minus negative 30 would be positive 30x. And then the minus 7 comes down. The next thing to do, look at the first term again. X squared times what gets me negative 13x squared? Be negative 13, wouldn't it? Negative 13 times x squared be negative 13x squared, right? So I'm going to distribute that out. Minus 60 and 18 be not negative 58. Nope, 78. Back up. 12 times, yeah, 78. That's right. And then positive 130. Subtract. Goes away. Here's the good thing. It doesn't matter what's left because that's the remainder. And we don't care what the remainder is. All we care about is up here, we've got what our oblique asymptote would be. Our oblique asymptote is going to be y equals 3x minus 13. And you've got to do the long division to find that. I'll show you the picture with the graphing calculator because it's pretty neat looking. And it kind of helps you understand what's going on. So I'm going to graph that original function that we had there, which was 3x cubed plus 5x squared minus 7. So I'm going to graph that. Parentheses 3x raised to the third plus 5x squared minus 7 plus 5x squared plus 5x squared minus 7. Close parentheses divided by parentheses. X squared plus 6x minus 10. X squared plus 6x minus 10. Here's the original graph. I'm going to graph the oblique asymptote on there, which we found was 3x minus 13. So on my calculator, I'm going to got 3x minus 13. If I zoom out a little bit, it makes it even more pretty. Look at how that oblique asymptote is shaping that little V shape up there. That's what an oblique asymptote does. Just like a horizontal asymptote shapes it, a vertical asymptote shapes that. Yes, part of the graph does cross that oblique asymptote. That's possible. That can happen. Okay. Horizontal asymptotes or vertical asymptotes are rarely crossed, but obliques get crossed from time to time. Okay. And not much to that. All right. Now, let's review our little rules that we have here. Let's go back to the start. Domain. When are we going to find domain? Before we simplify. At the very beginning, as soon as we get the problem, if it asks for the domain, we're going to look for the domain. Don't do anything else to it. Just do the domain. Factor the denominator, set it equal to 0, solve it. Then we're going to simplify the fraction. So that involves factoring the numerator as well and then canceling out matching factors. And then the next thing that we would look for would be vertical asymptotes. They are going to be what's left over in the denominator. If there's everything's left over, that's okay. We may have several vertical asymptotes, but they're always going to be there if there's something left over in the denominator. Okay, so always going to have a vertical asymptote if there's some x's left in the denominator. The next thing we look for after the vertical asymptotes is the horizontal asymptotes, and there are two scenarios. When the degrees are smaller on top, it's at y equals 0. When the degrees are equal, it's the ratio of the leading coefficients. Always reduce that fraction if at all possible. And then the other scenario is if the degree of the top is 1 more than the degree of the bottom. So that's like cubed over squared or fourth over third or fifth over fourth, that sort of thing. Then you're going to have an oblique asymptote, and you got to do long division to find that. If the degrees do anything else, It's okay if you don't have horizontal asymptotes or oblique asymptotes. You won't always have them. Will you ever have horizontal and oblique together? No, never, ever will you have horizontals and obliques together. Let's look at an example. Or 2, maybe 3, or 4, or no. Okay, look at some examples of this and see if we can build all those pieces to this. So, state the domain. Asymptotes. And graph on calculator. All right, so we're going to graph it on the calculator as well. So, all right. No idea what example we're on. I think it's E. Is that right? Yes, it is. Way to go. Know my alphabet. Small victories, folks. Small victories. All right. Here's our function. First one. Let's unleash x plus 1 over 2x squared plus 5x minus 3. Okay. So we're going to state the domain of that. We're going to do vertical asymptotes. We're going to do horizontal asymptotes. We're going to do oblique asymptotes if that has either one of those, either horizontal or obliques. We haven't decided yet. And then we're going to look at the graph of it. Okay. So the first thing that I'm going to do is find the domain. So let's find the domain. How do we do that? Say again. Where of what? The bottom part. Yeah, that's right. So 2x squared plus 5x minus 3 equals 0. And do an x method for that. The -6 and 5. What does that? 6 and -1. Good job. Can't take the shortcut here, so I'm going to have to do it the long way. 2x squared plus 6x minus 1x minus 3. Group. That would be 2x, x plus 3, -1, x plus 3. So our factors are 2x minus 1 and x plus 3. A lot of people want to skip that step and just go ahead and do the equations. That's fine, but you got to remember those factors because we may need them to simplify with. So don't forget that factored form is important when you go to simplify the fraction. It doesn't really do anything this time, but it's handy to have those. So we got 2x minus 1 equals 0, x plus 3 equals 0. That's going to be 1/2 and -3. So our domain in set notation, it's an easy way to do it. It'd be -3. X can't be -3 or 1/2. In interval notation, what would it be? You got to be able to do both. So. What's our interval notation for that? We're just cutting out the number 3 or -3 and 1/2 from all real numbers. To -3. Good job. Good job. Yeah. So there's our domain. That's a very important piece. Very useful. Then I look at the function in factored form to see if there's anything that cancels out. Is there anything that cancels out here? No. So no simplifying happened. It's okay. That's not the end of the world. That doesn't mean we can't keep going. So the simplified version is just the original version. Okay. So doesn't really help us to have it in factored form, but we looked at it just to make sure. So the next thing we want to do is our vertical asymptotes. vertical asymptotes. And from here on out, I'm going to abbreviate that as VA. So I don't have to write that out every time. And you're welcome to do the same. So vertical asymptotes, since nothing's simplified out of the denominator, I'm just going to take those two factors that are there and set them equal to 0 and get the equations. I've already done that over here. So my vertical asymptotes, since none of that canceled out, are the exact same equations. X equals -3 and x equals 1/2. Those are my vertical asymptotes. Had some of that canceled out in the fraction, then I wouldn't have everything that's in the domain in my vertical asymptotes. But sometimes, you know, it doesn't simplify, so everything's left over. Now, the next thing would be horizontal asymptotes, and I'm going to abbreviate that as HA, or oblique asymptotes, OA. Remember, it can't be both of those. It's only going to be one of those or neither of those. Okay, so looking at the original, what's the degree of the numerator? What's the exponent on this x right here? 1. So the degree of the numerator is 1. The degree of the denominator is 2. So which one of those does it fit? Horizontals or obliques? Horizontal. So it fits this rule. Scenario A. The degree of the numerator is less than the degree of the denominator. So that automatically means my horizontal asymptote is y equals 0. And we like that when that happens. If we have a horizontal asymptote, what does that mean about the oblique asymptotes? There's not any. So I'm just going to write none right there. Just to remind myself, hey, you got a horizontal, you can't have an oblique. Doesn't work, you can't do that. Okay? So we found vertical asymptotes. We found a horizontal asymptote. Turns out there's no oblique asymptote. And now we're going to look at the graph of that. That's all we've got to do left. That's all that's left on this problem. So I'm going to go back to the original form and use it to type into graph since nothing's simplified. Technically, if you're looking at the graph, even if it did simplify, the graph of the simplified version and the graph of the unsimplified version are exactly the same. They will always be exactly the same. So when I look at the graph, I usually just type in the original anyway. Okay, so you got to be careful about this. You're going to want to use parentheses for the numerator, which our numerator was x plus 1, divided by parentheses, and then the denominator was 2x squared plus 5x minus 3. Excuse me. And then I'm going to hit graph, and I'm going to hit zoom 6 because I zoomed out earlier. This one's got some funky stuff going on. It's got 3 pieces to it, but how many vertical asymptotes did I have? I had 2 of them, right? Can we see where they're at in our graph there? We can see that there's the x equals -3, and then over here, that's our x equals 1/2 that's happening there. So we see how it's split it apart. And then we got our horizontal asymptote, y equals 0, that's running right through the middle there. So that's the graph. And you can usually verify the things that you find by looking at that graph. We can see how it shaped it. All right. Let's do another. Same rules. Let's do f. F of x is equal to let's do 4x minus 3 over x plus 1. Really, really simple looking one. We're going to do the same things. We're going to find the domain. We're going to get our asymptotes, vertical, horizontal, obliques, and then look at the graph of that. So very simple looking rational function, but it's still a rational function nonetheless. So let's get our domain first before we do anything else. So how do we find our domain? So x plus 1 equals 0. And no factoring to do here. It's just a plain old x minus or x plus 1. So we're just going to solve that. X equals -1. So our domain is all x's as long as x does not equal -1. What's the interval notation for that? A little easier interval notation this time. Let's do -1. Yeah, sorry. Knew what you meant. And then -1 to infinity. It's a little easier domain on that one. The interval notation is a little easier. Be able to do both, kind of as always. And then the next thing we want to look for is to see if we could simplify that fraction. Does it factor in any way, shape, or form? No. So good news is we don't have to simplify. It's good. Way to go. Vertical asymptotes. Since it didn't simplify, where's our vertical asymptote? X equals -1. That's the equation of the vertical asymptote because nothing simplified. And then we got to decide about horizontals or obliques. What's the degree of the numerator? 1. What's the degree of the denominator? Ooh, they're the same. So that's scenario B for horizontal asymptotes, which says that the horizontal asymptote will be at the ratio of the leading coefficients. The leading coefficients are 4 and that 1 that's in front of x. So it's 4 over 1, which is 4. And because we have a horizontal, we don't have any obliques. They can't exist together. Stormtroopers and Jedis can't exist together, so they don't go together. All right, graph. Let's look at the graph. This one's a little easier to type in because it's pretty short. Parentheses 4x minus 3 divided by parentheses x plus 1. Graph. And we see the horizontal asymptote and the vertical asymptote at -1. We can see that happening right there. And then the horizontal at 4, we can see happening right there. So we see the picture of what's going on, how it's shaped by those asymptotes. Not bad, pretty easy one there, since it didn't do anything. It's always fun when it doesn't do anything. All right. Example G. G of x this time. Let's do x cubed minus x. Yeah, x cubed minus x over x squared plus 2x plus 1. Yeah, that's a fun one. A little bit more going on with this one. Try to kind of ramp it up a little bit here before we finish up. So what do we do first? I'll kind of help me along the way here so that you do portion of the lesson. What do you do here? Find the domain. How we do that?
Denominator equals 0.
So x squared plus 2x plus 1 equals 0. That's a good start. And how am I going to try to solve that? X method of factoring, going to multiply to be 1 and add to be 2. 1 and 1. So that's x plus 1 and x plus 1. So I'm just going to solve that once and get the domain is x cannot equal what? -1. Well, we've seen that in domain in the interval form already. I'm just going to copy down what we've done before. So there's our domain. Well, that one factored a little bit more. Does the numerator factor any? Because it's got more going on it than the other problems that we did have. So how does that numerator factor? Is there a GCF? Be x and x squared minus 1, wouldn't it? But what do we know about x squared minus 1? It's a difference of squares. Ooh. So there's the factored form of the numerator. So hidden underneath all of that nothingness is some stuff that does something. So what cancels out? The x plus 1 cancels out this x plus 1 and leaves us with a simplified version of x minus 1 over x plus 1. So that means our vertical asymptotes, do we still have one? Yeah, we still got some stuff in the denominator, right? So that denominator, x plus 1 equals 0. We still happen to have a vertical asymptote at x equals -1. Because we still had that dude left over in the denominator. So that's why we still got that as a vertical asymptote. Even though one of them canceled out, both of them didn't. All right. Now the fun part is the horizontal asymptotes or the oblique asymptotes. I'm just going to do that up there so we don't have to scroll so much. Again, I can look at the original or I can look at the simplified version. I'm going to look at the original because the degree is easier to get on the original, right? What's the degree of the original numerator? 3, the degree of the original denominator. 2, so that's 3 over 2, that's 1 more, right? So that means, what about our horizontal asymptotes? There isn't one, so but there is an oblique asymptote here. So none on the horizontals this time, and we have an oblique asymptote. So this is where we've got to do that long division. We can do that long division with either the original version or the simplified version. If you use the simplified version, you got to multiply it back out. It doesn't matter which one you do it with, so I'm just going to save myself the work of having to multiply it back out and just use the original. It works the same way. So that's what my plan of attack is. You might not hear any other professor tell you that, but why do extra work when you don't have to? So I'm going to set up my division problem. X squared plus 2x plus 1 into x cubed. I don't have an x squared term, so I got to put 0x squared minus x plus 0 in there. So I'm just putting all the missing pieces, and then I'm trying to multiply this out. So what times x squared will get me x cubed? X. So that's x cubed plus 2x squared minus x. Subtract. Those go away, and there is a negative 2x squared, and then nothing. 0x, because negative x minus negative x is 0x. And then what times x squared will get me negative 2x squared? Negative 2. So minus 2 goes on there. Multiply. Minus 2, subtract. Those go away. Technically, we don't care what happens after that because that's just going to be a remainder anyway. And the only thing we're worried about is y equals x minus 2. That's our oblique. Oblique asymptote you should be able to find it in two steps of long division. But you don't have to do the full long division, just 2 steps of it should get you a slope-intercept form of an equation, and that is your oblique asymptote. So let's look at the graph of this, and again, I'm just going to go back to the original, x cubed minus x over x squared plus 2x plus 1. So again, parentheses, x raised to the third minus x, close parentheses, divided by parentheses, x squared plus 2x plus 1. I'm going to go ahead and type in the equation of my oblique asymptote because I want to see what it looks like. Oh, man, that's a nice picture there. So we got the blue parts are our function, our rational function. The red part here, or this other line, it's not really red. It's projector screen here, but that's our oblique asymptote. What really does a good job showing it up, showing the shaping of the graph there. And then we see our vertical asymptote right here. Not bad. Okay. Not bad. Questions about rational functions and rational expressions? Yeah, I seem to maybe have caught on, but I don't think the factoring review have to lot. All right. Well, let's call it a night. Problems that you might want to look at in your textbook. I believe this is the correct page number. We've changed versions of the textbook a couple of times. Does anybody have their textbook with them? You do? Can you turn to page 346 in there? Whatever. I know they're leaflets, so the bottom page should be around 346. Is there like a summary box, like a green box at the bottom of that page? Yeah, and it does say something about rational functions and things, or does it? 346. Yeah. Here. If you got the textbook on page 367, is a summary box about the graphs of rational functions. So it's a handy thing. Or if you want to shoot a picture of it in someone else's textbook, they've got a textbook on in the library that if you want to go by and take a picture of, Miss Amy can let you do that. That can be helpful. So the summary box on page 367 is a good kind of just summarizes everything we did. In R5, the problems, 1 through 77 would be a good ones. 3, 5, 1 through 105, any of those odd ones there. Just kind of a little bit of each thing there involved.